Hi, so in this lecture, a short lecture, we will prove a very important theorem that is called something uniqueness of algebraic closure. So the theorem statement is the following: that suppose F is a field and K1 and K2 both are algebraic closure of F, then K1 must be K isomorphic to K2. So what does this mean, K isomorphic? K isomorphic means I must get a isomorphism from K1 to K2 via sigma such that, so both are extension of F such that sigma restricted at F must be identity. So basically these diagrams should commute. Okay, so you can assure that, suppose you have any particular field F. So for any particular field, the maximum algebraic extension that one can think of is the algebraic closure. Okay, so the maximum one that one can algebraic extension that one can think of. In fact, the existence of algebraic closure is solved via Jones' lemma using the maximal condition. Okay, so all right, so this is the largest one that one can think of. Now to prove it, let us consider that. So before, let us prove a very small helping lemma. The helping lemma says that, for example, consider that F is a field and it has two extension, one is L and another one is K, where K is algebraic extension and L is algebraically closed. So both are two extensions. Then there exists an isomorphism from K to L, there is sigma, such that sigma restricted at F is identity. That means these diagrams should compute. Okay, so let us try to prove it. Here also we use this very interesting Jones lemma. So how to prove it? Let us go on. Suppose we consider the collection of E comma sigma such that E is an intermediate extension, that is K over E over F, and sigma is from E to L such that sigma is identity at F is identity. So the first question is that sigma is non-empty. So to prove sigma is non-empty, so let us consider that here is my K and is algebraic extension of F. So that of course there is alpha belongs to K, right? So that means alpha must have a minimal polynomial P alpha x here. Now again there is an extension of L where L is algebraically closed. So this P alpha x must be split in L. So that means there exists some beta belongs to L such that P alpha of beta is 0, right? So you can see that now in between K and F and K, I have K alpha and F. Okay, so K alpha, the elements are given as F of alpha such that Fx belongs to the ring of polynomials Kx. So then we can introduce a map from k alpha to L itself via sigma, where sigma is mapping from k alpha to L such that sigma of f of alpha is mapping to f of beta itself. So that means basically alpha is mapping to beta. That's a key point. Okay. So then we can consider k alpha and sigma this tuple. So that means for any alpha belongs to k, we have k alpha comma sigma belongs to this set. So this is non-empty. So this is done. Next question is that sigma is a partially ordered set. Okay, so to define a partial ordered set, we need to define a partial order relation. So this less or equals partial order relation. So define, let's say e1 comma sigma 1 is partially is related to less or equal to e2 comma sigma 2 if e1 is an intermediate extension of e2 k and f, and sigma 2 restricted at e1 equal to sigma 1 itself. Okay, now if we consider a chain of, let's say, e1 comma sigma 1 e2 comma sigma 2, then again less or equal to et e3 comma sigma 3 and so on, then I can choose a maximum one, right? That is e1 en comma sigma n. Suppose it is in a final chain, so I can take this particular element as well, because we have e1 subset of e2 subset of itself en and sigma n restricted at en minus 1, it is sigma n minus 1. Now again if we restrict it again up to n minus 2, it's again e of n minus 2, that is sigma n minus 2, and so on, it will go on. Okay, so that means it is a maximum, so it is a maximum element of any particular chain. So that means any particular chain is an upper bound. Alright, now the thing is that we have to show that means as it is upper bound, so that means it must have a maximal element. So it must have a maximal element. Let us call the maximal element as e tilde comma sigma tilde. Okay, so we have here again e tilde comma sigma, sorry, e tilde from here to k, okay, not k as well, there is, yeah, let's say it is up to, yeah, okay, just so for example, suppose it is my k, this is my f, it is my l, so and in between there is something f of, there is something e tilde. Alright, now my claim is that, so there is sigma itself, sigma tilde itself. My claim is that k must be same as e tilde. Okay, so there is extension like this. So suppose not, so let small x belongs to k such that small x naught does not belongs to e tilde. So then we can again construct a field e tilde over x naught, which is in between k, e and e tilde is itself is my f. But so again, so x naught belongs to k, there must be some p naught x here, and it will completely get split over here. So that means there exists, so it is my sigma tilde. So that means from e tilde of x naught, I will again get a sigma double tilde, such that sigma double tilde restricted at e tilde, this is itself sigma tilde. But this is not true, because sigma tilde, e tilde comma sigma tilde is the maximal element. So that contradicts the maximality of E tilde comma sigma tilde. Okay, so that means there exists a map. So K to F, here is my L, there is a map sigma. Now for we can define sigma, just remove the tildes or all these signs at all. So there is some sigma is there, such that sigma is restricted at F is identity. This is true for algebraic any, but make sure that it is algebraically closed. Okay, so now just see one thing. So from K1, here is my F, here is my L, I'm sorry, here's my K2. So there is one sigma which is mapping to sigma is monomorphism from K1 to K2 that preserves F. So of course this is injective. Now to show that it is surjective as well. Okay. So now in order to prove that alpha is, this particular sigma, this is isomorphism, what we have to do. So let us consider that. So let us have another setup. So K from here is sigma to L and F is like this. So this diagram commits. So let's take small l belongs to capital L. So small l is algebraic over F. So small l is algebraic over F. So that means so small l is algebraic over F means you see that sigma of K, this is inside L, right? Sigma of K, it is inside L. Now we all know that sigma K is inside L, right? Now if we take small l belongs to P of X, so small x must have a minimal polynomial Px that belongs to F of X, right? Now K is algebraically closed. So that means Px, this must be splitted in Kx in some different roots. So Px must have, let's say, alpha, let's say alpha 1, alpha 2, and so on up to alpha this one up to alpha n. Right? Now, if we apply sigma of alpha 1, each alpha I, so what should be this? So this will map to some root of L, some root of so of course there is some now if I consider the all the possible values of sigma alpha I over there, so this must be some root of Px in Lx. Now there are only these many roots are possible, right? So at least one alpha j must be there that will map to L, because if all the elements, let's say except means in Lx it might have some other roots, for example let's say beta 1, beta 2 up to beta m comma L. Okay, so it must be that if we consider that all alpha i's must maps somewhere here, and of course there are as the degree of Px, let us say it is n, so there must be also m plus 1, this must be 1 n, right? Because of course m equal to n minus 1. So as the number of roots should be same, that means, and sigma is injective, so at least one alpha j must map to L. So that means this particular sigma of alpha j I'll choose L. So this sigma is basically an isomorphism and it preserves, so sigma belongs to isomorphism from K to L that preserves F. Okay, so this completes the proof. Thank you very much.